Hello everybody. Today's topic is complex power series. Before going to the topic, we learn about what is sequence and series. A sequence of complex numbers Z1, Z2, so on Zn is an assignment to each positive number n. So means that if you write a number of values in order, that is Z1, Z2, so on Zn, always Z is a complex number. So that's why we called as this sequence is called complex sequence. A complex number Zn is called the term of the sequence. A sequence is denoted by set of Zn and it is said to be convergent if limit n tends to infinity. Zn is equal to C. C means it's a finite quantity. Otherwise it is said to be a divergent. If this limit value is infinity or plus or minus infinity, we called as it is divergent. Otherwise limit n tends to infinity, Zn is equal to C. What is Zn here? Zn is the nth term of the sequence. You can take the nth term of the sequence, apply the limit as n tends to infinity. If you get the value is finite, then that sequence is convergent sequence. Otherwise it is divergent sequence. So summation n is equal to 1 to infinity, Zn is equal to Z1 plus Z2 plus so on Zn be an infinite series of complex numbers. So addition of the sequence is called the series of the complex number. Here Z1, Z2, so on Zn are the complex numbers. So that's why we called as complex series or complex numbers series. Next definition is power series. What is called power series? A power series in powers of Z minus Z0 is a series of the form summation n is equal to 0 to infinity an Z minus Z0 whole power n. Means that the series write by using Z minus Z0 terms and it is multiplying with a constant an. So if you apply from n is equal to 0 to infinity, we get a0 plus a1 into Z minus Z0 plus a2 into Z minus Z0 whole square plus so on. This type of series are called power series. Next definition is region of convergence. Region of convergence of series is the set of all points of Z for which the series converges. Then that series is called region of convergence. So in the set of all points in the series where the region is convergence, means which point the region is convergent, then that point is called region of convergent. Next one, radius of convergent. If summation an z power n converges for mod z less than r and diverges for mod z greater than r, then r is called the radius of convergence of the power series. Here capital R is the radius of the series. If mod z means x square plus y square, circle is less than, means inside the circle is converges. Mod z greater than r means outside the circle, whatever the region is given, so outside the region the series is divergent. So then r is called a radius of convergence of the power series. Next one is, and continuity for that, mod z is equal to r is called the circle of convergence of power series. If capital R is the radius of convergence of the power series, summation an z power n, then the power series converges uniformly for mod z less than or equal to r1 less than r. Means that if you take any region of radius r1, so then the series the mod z is converges for r1, means r1 is mod z is less than or equal to r1, it is less than r, means below the r if you take any region, that region radius is r1, then we can write uniformly it is converges mod z less than or equal to r1 less than r. So these two definitions are very important for radius of convergence and circle of convergence for the examinations. Next one is Taylor's theorem. Main topic of the complex power series is first topic Taylor's theorem, next topic Lorentz theorem. First one is Taylor's theorem. The statement for this Taylor's theorem is if f of z is analytic at all points within a circle C0 with center at A and radius R, then at each point z within C0, f of z is equal to f of a plus f dash of a into z minus a by 1 factorial plus f double dash of a into z minus a whole square by 2 factorial plus so on, plus nth term f power n of a means nth derivative of f of a and into z minus a whole power n by n factorial plus so on. It is an infinite series. So this is called this series Taylor series. This is called Taylor series expansion of f of z in powers of z minus a in powers of z minus a or about z is equal to a. So here circle is given, circle with center at a and radius r and the curve is C0. In this region we define the Taylor series for f of z. So f of z is here analytic. So f of z is equal to f of a plus f dash of a into z minus a by 1 factorial plus f double dash of a into z minus a by 2 factorial plus so on. So based on the Taylor series, we have to write the another series by substituting a equal to 0 in the Taylor series. We get f of z is equal to f of 0 plus f dash of 0 into z by 1 factorial, because of here a value is 0, so that's why we get z by 1 factorial plus f double dash of a, f double dash of 0 into z square by 2 factorial, a value is 0, plus f triple dash of 0 into z cube by 3 factorial plus so on. This is called McLaren series expansion of f of z. If you substitute a is equal to 0 in the Taylor series, we get another series that is called McLaren series. So standard McLaren series are e power z sin z cos z 1 by 1 plus z 1 by 1 minus z etc. So now we can write the expansions for that. E power z is equal to 1 plus z square by 2 factorial plus z cube by 3 factorial plus so on, z power n by n factorial plus so on for all z mod z is less than infinity. So here radius of convergence is infinity. And going to the sin z, expansion for the sin z, our series for the sin z is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus so on for mod z is less than infinity. So that is the radius of convergence is here infinity. These all are e power z sin z cos z, radius of convergence is infinity. So now z cos z is equal to 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus so on for mod z is less than infinity. So now going to our main important expansion 1 by 1 plus z. 1 by 1 plus z expansion right by using binomial series 1 plus z whole power minus 1. The expansion is 1 minus z plus z square minus z cube plus z power 4 minus so on for mod z less than 1. Here the series is converges for mod z is less than 1. Here radius of convergence is 1. So whenever you have to write the possibility for mod z is less than 1, this series is valid, otherwise this series is not valid. So whatever the value in the place of z, that value must be less than 1, then only the series is valid. Okay, then next one 1 by 1 minus z, 1 minus z whole power minus 1, 1 plus z square plus z cube plus z power 4 plus so on for mod z less than 1. Here also radius of convergence is 1. This series is valid for the z for mod z is less than 1. So next expansion is log of 1 plus z equal to expansion z minus z square by 2 plus z cube by 3 minus z power 4 by 4 plus so on for mod z is less than 1. Here also radius of convergence is 1. So this series is valid for mod z less than 1 only. Now discuss the examples. Expand e power z as Taylor series about z is equal to 1 and about z is equal to 3. About z is equal to 1 means you can write a Taylor series in powers of z minus 1, and about z is equal to 3 means you can write the Taylor series in powers of z minus 3. So first one, f of z is equal to e power z. Here you can write the Taylor series in two ways. First way is which power you can write, z minus 1 power series we want. So directly we can take z minus 1 is equal to w, z is equal to 1 plus w. Substitute in our given function e power z is equal to e power 1 plus w, because of we are substituting z is equal to 1 plus w. So then all of you know e power a plus b is equal to e power a into e power b. So e power 1 into e power w. So e power 1 is constant, e constant right outside. We have a expansion for e power z. In the place of z we have w. So by using this expansion we can expand e power w. E power w expansion is 1 plus w square by 2 factorial plus w cube by 3 factorial plus so on. Same as it is I am writing here. So then substitute the w value, w is equal to z minus 1. We get the series in powers of z minus 1. So 1 plus w value z minus 1 plus z minus 1 whole square by 2 factorial plus z minus 1 whole cube by 3 factorial plus so on. Then this is valid for modulus of z minus 1 less than infinity, because of in the place of z we have z minus 1. So that's why mod z minus 1 less than infinity. Next one, put z minus 3 is equal to w. Why we take z minus 1, 3 is equal to w? Next series write for z minus 3 powers. So that's why we can write z minus 3 is equal to w. Z is equal to w plus 3. E power z is equal to e power w plus 3. Then separate the values e power w into e power 3. E power 3 is constant right outside, and write the expansion for e power w, 1 plus w square by 2 factorial plus w cube by 3 factorial plus so on. You can write w or omega, any variable you can take it. And in this expansion substitute the w value is z minus 3, 1 plus z minus 3 plus z minus 3 whole square by 2 factorial plus z minus 3 whole cube by 3 factorial plus so on. If mod z minus 3 is less than infinity for all z. Why? Because of e power z expansion is valid for mod z is less than infinity. In the place of z we have z minus 3. So that's why mod z minus 3 is less than infinity for all z. This is one of the procedures to solve a Taylor series directly, but by using the series we can solve it. That is by Taylor series. First you have to write the series for f of z. F of z is equal to f of a plus z minus a into f dash of a plus z minus a whole square f double dash of a by 2 factorial plus z minus a whole cube f triple dash of a by 3 factorial plus so on. This is a standard series for Taylor's. So first you have to write it. After that we can write the series for about z is equal to a. This is a Taylor series about z is equal to a or in powers of z minus a. We know that, but in the given problem first one write for z minus 1. So here a value is 1. So if f of z is e power z, we need here derivatives, at least 3 or 4 derivatives for each any given function. So that's why we can find the derivatives. First order derivative f dash of z is equal to e power z, because of e power z derivative is e power z only. Next f double dash of z derivative is e power z only. E power z derivative e power z. F triple dash of z, again second order derivative is e power z. So we get the 3 derivatives and find the f of a means z is equal to a. You can substitute it. F of a equal to f of 1, that is equal to e power 1, that is equal equal to E. Next, f dash of A, that is f dash of 1, e power 1 value is E. Next, f double dash of A, f double dash of 1 value is e power 1, that is also equal to E. Next, f triple dash of A equal to f triple dash of 1, that is equal to e power 1, that is equal to E, and so on. We need to find at least 3 or 4 derivatives to the given function and substitute the A value. We get the f dash of A, f double dash of A, and triple dash of A. All the derivatives you can substitute in the Taylor series. We get f of z is equal to f of 1. Because of f of A, we need first value is f of A value is 1. F of 1 plus z minus A value 1, z minus 1, f dash of 1 plus z minus 1 whole square, f double dash of 1 by 2 factorial plus z minus 1 whole cube, f triple dash of 1 by 3 factorial plus so on, and substitute the values. E power z, f of z is equal to e power z, and f of 1 value is E plus z minus 1 into E plus z minus 1 whole square by 2 factorial into E plus z minus 1 whole cube by 3 factorial into E plus so on. E is a common term from all the terms. You can common E. We get the series expansion in powers of z minus 1, that is 1 plus z minus 1 plus z minus 1 whole square by 2 factorial plus z minus 1 whole cube by 3 factorial plus so on. This is another procedure to solve a Taylor series. Actual method is to solve Taylor series by using the formula for f of z. Otherwise, you can use the expansion directly by using this method also. And going to the next example. Expand log z by Taylor series about z is equal to 1. So first one, f of z is equal to log z. Here about z is equal to 1 means the Taylor series expansion right for in powers of z minus 1. So you have to find the derivatives. F of z is equal to log z, and directly you can find the f of 1 value. Log 1 value is 0. F dash of z, log z derivative is 1 by z. So f dash of 1, we can substitute z is equal to 1. 1 by 1 equal to 1. F double dash of z, 1 by z derivative is minus 1 by z square, because of we find the derivative for z power minus 1. So the x power n derivative is n into x to the power of n minus 1. So minus 1 z power minus 1 minus 1. That's why we get minus z power minus 2. It becomes to minus 1 by z square. That is f double dash of 1. A value is 1 equal to minus 1 by 1 equal to minus 1. Next one is f triple dash of z, third order derivative for this z. So minus 1 by z square derivative is minus is there. Z power minus 2 derivative, minus 2 into z power minus 3. So that's why minus into minus plus 2 by z cube. Next f triple dash of 1 is 2 by 1, that is 2. Next fourth order derivative for f of z is, here already constant 2 is there. Keep it outside. 1 by z cube derivative means z power minus 3 derivative is minus 3 z power minus 3 minus 1, that is 2 into minus 3 by z power 4 minus 6 by z power 4. Fourth order derivative at 1, that is equal to minus 6 by 1, that is minus 6. All the values substitute in the Taylor series. First you have to write the Taylor series. F of z is equal to f of a plus f dash of a into z minus a plus f double dash of a into z minus a whole square by 2 factorial plus f triple dash of a into z minus a whole cube by 3 factorial plus so on. After that you can substitute all the values to the given series, that is f of 1, f dash of 1, f double dash of 1, f triple dash of 1. Fourth order derivative of f of z at 1, you can substitute it and a value is 1. So we get the series is f of 1 value is 0, so that's why I substitute here 0, and f dash of 1 value is 1 and z minus 1 a value is 1 plus f double dash of 1 value is minus 1, z minus 1 whole square by 2 factorial plus f triple dash of 1 value is 2 into z minus 1 whole cube by 3 factorial. And Fourth order derivative value is minus 6 into z minus 1 whole power 4 by 4 factorial. So the log z expansion in powers of z minus 1 is z minus 1 minus z minus 1 whole square by 2. Why we get here 2, we are writing here 2 factorial, and it is a value is 2. Next, 2 by 3 factorial, 2 by 6 value is 3, so z minus 1 whole cube by 3. And next one is negative sign, minus 6 is there, minus z minus 1 whole power 4 by, here 6 by 24 factorial value is 24, 6 by 24 is 4, 1 by 4, so that's why z minus 1 whole power 4 by 4 plus so on. This is the procedure to solve any given function by using the Taylor series. Next one is expand f of z is equal to sin z in Taylor series about z is equal to pi by 4. Means that you can write the Taylor's series to the sin z in powers of z minus pi by 4. Here a value is pi by 4 and f of z is sin z. First we have to find f of a, that is f of pi by 4. So sin pi by 4 value is 1 by root 2. F dash of z, sin z derivative is cos z, and f dash of a, f dash of pi by 4 is cos pi by 4. Cos pi by 4 value also 1 by root 2. Next, second order derivative. First order derivative is cos z, derivative is minus sin z. F double dash of a is equal to f double dash of pi by 4 is equal to minus sin pi by 4 equal to minus 1 by root 2. And f triple dash of z is equal to minus cos z, that is sin z, derivative is cos z. Already negative sign is exist in the second order, you can keep it here also, minus of sin z, derivative is cos z, so that is minus cos pi by 4 minus 1 by root 2. Fourth order derivative is minus cos z, derivative is minus sin z, minus of minus plus sin z. So fourth order derivative of f of z at a equal to sin pi by 4 1 by root 2. All the values substitute in the Taylor series. F of a value, f double dash of a value, f dash of a value, f triple dash of a value, fourth order derivative of f of a value. You can substitute in the Taylor series, and a value is here pi by 4. We can write the Taylor series in powers of z minus pi by 4. We are writing the Taylor series expansion for the sin z in powers of z minus pi by 4. Means here z minus in powers of z minus a value is pi by 4. I am substituting f of a value 1 by root 2, f dash of a value also 1 by root 2, z minus a value is pi by 4 plus f double dash of a value is minus 1 by root 2, z minus pi by 4 whole square by 2 factorial plus f triple dash of a value also minus 1 by root 2, z minus pi by 4 whole cube by 3 factorial plus fourth order derivative is 1 by root 2 into z minus pi by 4 whole power 4 by 4 factorial plus so on. All the terms having 1 by root 2, so that's why we are common the 1 by root 2 and write the Taylor series expansion for in powers of z minus pi by 4. That's all for today.